Good morning, students. Welcome to the class on photochemistry of aromatic compounds. Though benzene is more stable, generally it doesn't involve in addition reactions under normal conditions, but benzene do involve in many chemical transformations under photochemical conditions. We will see one by one. When light is passed on to benzene ring, one of the double bond in benzene will be excited, so it generates 1 comma 2 diradical. This 1 comma 2 diradical will involve in a 3-membered ring with this carbon. So it involves in 3-membered ring formation. This is the previous radical and we are generating one more radical here. So the double bond, 2 electrons in this double bond, one will be polarized towards this carbon, one will be polarized towards this carbon. This electron and this electron, they will combine to generate this bond. This is the previous bond. Now this can be involved in a resonance. When it involves in resonance, of course, we have this 1 comma 3 diradical. Now this will be converted to fulvene. This is called fulvene. How do we generate this? Break this bond. So it generates the 5-membered ring and then subsequent double bond formation. Because this compound is generating fulvene, it is called pre-fulvene. It is called pre-fulvene. Now, instead of generating fulvene, if these two radicals undergo bond formation, that results in this molecule. This can be written as this is called benzoylene. When we extend this carbon upside, so drag this carbon top so that we can clearly visualize this structure. So this is the 3-membered ring. This is the other 3-membered ring. So benzene under photochemical conditions, after generating this 1 comma 3 diradical, after generating pre-fulvene, it can be converted to fulvene or it can be converted to benzoylene. Not only this, benzene can also be converted to prismane via dibenzene. How? For example, this 1 comma 3 diradical is rearranged as 1 comma 4 diradical. If it is rearranged as this 1 comma 2 diradical is rearranged as 1 comma 4 diradical with resonance, then the bond formation between these two radicals generates dibenzene. Dibenzene under further photochemical conditions, these two carbons will form a bond, these two carbons will form a bond. So it undergoes 2+2 cycloaddition under photochemical conditions to generate prismane. So under 2+2 cycloadditions under photochemical conditions, divar benzene undergoes 2+2 cycloaddition to generate prismane. Now, what is the use of these photochemical conversions? These photochemical conversions are utilized in isomerization of substituted benzenes. When benzene is having substituents under photochemical conditions, these substituents can be isomerized in different ways. For example, this 1,2 dialkyl benzene under photochemical conditions, if it forms benzoylene, there are two substituents 1,2. We can convert this to 1,3 dialkyl substitution. 1,3 dialkyl substitution. How this divar benzene generated from 1,2 to 1,2 dialkyl benzene is now converted to 1,3 dialkyl benzene. We will give numbering to easily identify this. We need 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. This way we can easily identify the formation of this structure. So 1,2 dialkyl benzene under photochemical condition is now isomerized to 1,3 dialkyl benzene. Now we will have bonding between 1,2, but 1,3 bond will never exist. So break this bond. There will be bonding between 3,4, 4,5, 5,6, 6,1. But bonding between 2,6 carbons is not possible. So break this bond, this will generate a double bond. Break this bond, this will again generate one more double bond. One double bond is already there. So altogether we are regenerating the benzene structure. Now, what will happen if this 1,2 dialkyl benzene is converted to divar benzene, prismane? When this molecule under photochemical condition is converted to prismane, then this will undergo bond breaking in such a way the resultant compound will be 1,4 dialkyl. The resultant will be 1,4 dialkyl. So we need to realize the formation of 1,4 dialkyl from the prismane. It is always better to give the numbering. So break the bonds which will not exist in this cyclic form. We need 1 and 4 for these two carbons. So 1, 2, 3, 4, 5, 6. Again there is a bond between 6 and 1. So it becomes a cyclic system. In the cycle 1,6 bond will exist. So 1,2 bond will exist, 1,6 bond will exist, but 1,4 bond will not exist. So this is the one bond which will break. Then 3,4 bond will exist, but 3,5 bond will not exist. So this is the second bond we need to break. Sixth carbon will be bonded to either fifth or first, but not to second carbon. So when we break these three bonds, we will realize 1,4 dialkyl benzene. So the use of conversion of benzene to either fulvene structure, benzoylene structure or prismane structure is to isomerize the substituents. There are many possibilities. What we need to do is just practice under photochemical conditions. This 1, 3, 5 trialkyl benzene is converted to 1, 2, 4 trialkyl benzene. How do we realize this? How do we identify this? You just take either benzoylene or prismine intermediates, then give the numbering in such a way it gets the 6-membered cyclic system and break the bonds which are not which will not be there in the cyclic system. So that will give us these products. We can use either benzoylene or prismine. Both may be used or any one may be used to explain the product formation. And similarly, this 1, 2, 4, when it is treated under photochemical conditions, it may be again isomerized to 1, 3, 5 trialkyl benzene. This 1, 2, 3, 5 trialkyl benzene, tetraalkyl benzene, when it is treated under photochemical conditions, it is undergoing isomerization to 1, 2, 4, 5 tetraalkyl benzene. So just take any of these two structures, place the alkyl substituents and then break the bonds, give the numbering, break the bonds which will not exist in the cycle, so that we can easily identify the products. It is just a practice. So I suggest you to practice these photochemical conversions using either benzoylene intermediate or prismane intermediate. I'll give you one more method for the preparation of Dewar benzene. Under photochemical conditions, this 4 pi electron system will undergo disrotation so that it will have a bond across these two pi bonds. So it generates 4, 4 and then 5-membered fused ring system. Because it is the stereochemistry is given here. Here also we can identify the stereochemistries. Probably it will be like this. Here it should be below the plane. Then it is treated with lead tetraacetate. So we have discussed about the reactivity of lead tetraacetate during oxidations. Lead tetraacetate is known for decarboxylation. So in this case, it will undergo the anhydride, 5-membered anhydride will undergo decarboxylation. This side we have one decarboxylation, this side also another decarboxylation that generates a bond here. So this is Dewar benzene, or we can also write in this form. So this is how we can also generate Dewar benzene. Now coming to the photochemical reactions of benzene. Benzenes, benzene will also involve in 2 plus 2 cycloadditions under photochemical conditions. One of the double bond in benzene ring will involve in 2 plus 2 cycloadditions. Generally, when we have substituent, that carbon preferentially involves in 2 plus 2 cycloaddition over the other pi bonds. So this is the product. So you practice the product. When acetaldehyde is the unit is converted as acetol under photochemical conditions, this alkene will involve in 2 plus 2 cycloaddition with benzene ring. So it generates a 4-membered ring with acetol. Now, under the same photochemical conditions, or we can also use thermal conditions, it will involve in 6 pi electron electrocyclic ring opening either photochemical conditions or thermal conditions. It will involve 6 pi electron electrocyclic ring opening, 2 double bonds and 1 sigma bond. So this is the 6 pi electron electrocyclic ring opening. We have 6 carbons here, 2 carbons here. Altogether we will get 8 carbon system. And we have acetol here. Of course, acetol can be hydrolyzed back to the carbonyl. So the ultimate product is this. So benzene not only converts to benzoylene or prismine under photochemical conditions, it also involves in 2 plus 2 cycloaddition reactions. Under photochemical conditions, it involves in 2 plus 2 cycloaddition. You write the product. Then again, either under photochemical condition or thermal conditions, it involves in 6 pi electron electrocyclic ring opening reaction. So the 6-membered system, similar to the above problem, it will be converted to 8-membered ring. Because it is a triple bond, we will have a double bond here. So the 8-membered ring will be this one with 2 ester groups. With 2 ester groups. I'll give you one more practice problem. Benzene undergoes 2+2 cycloaddition with this succinimide alkene. It generates a 4-member. Of course, we also have a 5-member imide. When we look at the ring fusions, as we have discussed in the above problem, one ring fusion will be above the plane, other ring fusion will be below the plane. We also have a diene in the molecule. So again, it can be treated with one more succinimide under thermal conditions. So it undergoes a Diels-Alder reaction to generate a 4+2 cycloaddition, 4 pi electron plus 2 pi electron cycloaddition between this diene and dienophile. I'll write the product here. This is the 4-membered ring. These two are above the plane. These two are below the plane. The hydrogen here, they are above the plane. The hydrogens here, they are below the plane. Now this diene will undergo 2+2 with this dienophile. And as we know, it will be endoselectivity. So the amide ring will be towards the alkene for better endoselectivity. So benzene under photochemical conditions will involve in two plus two cycloadditions, 2 pi s plus 2 pi s, to give this 6 and 4 membered fusion system. It also involves in 4 pi s plus 2 pi s cycloadditions to generate this bicyclic systems. And now we also have metacycloadditions where it generates a 3-membered ring like this, and an alkene will add to benzene like this. This is called meta addition. This is the alkene. So this will give a complex structure. See, this is a 5-membered ring, this is a 5-membered ring, and we have a 3-membered ring on the top. So this can be rewritten like this. If you want to realize this structure from this, you just drag this ring like this. You just drag this towards right side so that we can easily realize this. So this is the 1, 2 carbons. So what are these metacycloadditions? What are these metacycloadditions. Under photochemical conditions, they will be converted take this 5-member like this. What will happen under photochemical conditions? There will be a bond between these two carbons. Then a 3-member ring will be generated here. Of course, this is unused double bond. So 2 double bonds will be used for metacycloaddition. 1, 3 carbons will involve in bonding with alkene. Then other 1, 3 diradical will involve in 3-membered ring generation. This is 1, 2. Now if you want to rewrite in a good looking conformation, then as I said, you just drag this carbon. So 5, 5, 5. There are 3 5-membered rings. This is the double bond. This is a 3-membered ring. And this is the 5-member. This 1,3 metacycloaddition with substituted benzenes then this alkyl group, around this alkyl group, this carbon and this carbon, they will involve in bond formation with the alkene. So obviously this carbon will be at the 3-membered ring. So when we write the product, this is a 3-membered ring, and of course this is the 5-membered ring which we are using. Now this will be at the 3-membered ring junction at this carbon. This alkene is undergoing bond formation with the 1 carbon that side and 1 carbon this side. Of course, unused double bond will be there. So this is how we need to write metacycloaddition products in a simple manner. I'll give you 2 more examples for metacycloadditions. These 2 are intermolecular metacycloadditions. Now we will see an example where benzene undergoes metacycloaddition intramolecularly. So the double bond is also there. It is there on the benzene ring. Now under photochemical conditions, it will be converted to you just take this conformation. This is the double bond and this double bond is in E configuration. So we are representing this E configuration. Now there will be a bond formation between these 2 carbons and these 2 carbons. Then this carbon and this carbon they will involve in this carbon and this carbon they will involve in 3-membered ring formation. So we can easily write the product when we rewrite this in this conformation. then the product from this cyclometa addition can be easily written. There will be bond formations between these two carbons, and there will be a three-membered ring here. Of course, there is another unused double bond. So this is how we need to predict the products in metacycloadditions. I'll give you the last example for photochemical reactions of aromatic compounds. This molecule undergoes cyclometa addition intramolecularly, and it generates a product like this. We have ester group here, ester group here, and we have hydrogen here. So this is how benzene involves in photochemical reactions.